Okay. So I'm going to be doing a bit of an overview intro, and then Aedan will get into some specifics, especially around North American codes. So the big ticket item here that I want to talk about is just acoustic quality and how it affects day-to-day amenity with occupants in buildings. The example I like to use is that people that have just bought their apartment or moving into a new development don't sort of sit back in their recliner and think, oh, don't you just love that 2-hour fire rating? What they like is that peace and quiet in their home, and especially with the cost of build and the cost of apartments these days, there's a higher expectation of amenity generally. And with lightweight timber buildings, as you may have experienced or you may have heard, there are some unique acoustic challenges, mainly because it's less weight. There's less mass for the energy to sort of dissipate in. And so you need to be able to coordinate that quite early on in the design and make sure you've got the right team and collaboration throughout everybody. And so I really am encouraging carefully designed projects. So one that helps minimize occupants' noise complaints over the long term, and it also helps developers in terms of their concern over lightweight developments and whether people will be cautious in purchasing. So well-designed buildings is what I'm preferring. Now, without a problem, there's no solution, and so there's a fairly easy problem in the Australian code, and it's just some of the code is just not up to scratch in terms of what people are expecting from amenity. So straight from the NCC, the building code, their goal is to have a nationally consistent, but it's minimum necessary standards for all health, safety, amenity. And so this minimum standard, when we sort of push back on the building codes board and say, we think the criteria isn't good enough, they say, well, it's only minimum. It's only to meet, the bare minimum especially for low cost housing. And so that's a real problem when you're trying to design a lightweight building, but even just a quality apartment. Now, the actual objective in the building code is I think is actually quite stringent, because it's trying to prevent the illness and loss of amenity to the occupants. So it's designing buildings, designing floors, walls, all the treatments around to not lose amenity. And so the question is, well, what is the standard? So the basic standard that you're probably familiar with, which is now part 7, previously part 5, is you have an airborne component in terms of how much sound travels through the air. And that's these RW descriptors and CTR descriptors, which we can get into, but they're single numbers that are trying to capsulate how much sound is transferring between. And for airborne, it's an RW or CTR greater than 50. And for an impact, it's an LNW, and it's a less than, and Aedan can get into some of that too, but it's the lower number is better for impact. And so they're the standard part F7 requirements. Now, just as a general, we won't get into too much specifics here in the intro, but in my opinion, a lot of the acoustic consultants around industry, the airborne criteria is very reasonable. It's sufficient. If you build to the airborne criteria, conversations, television, music, all that sort of noise within an apartment is fairly controlled. We rarely have noise complaints from that. If the building's been built to code, it's fairly suitable. There's no other way to say it, but the impact criteria is woeful. So please don't design for minimum. Now, normally conventional buildings with concrete can get away with it because their standard designs are already sometimes better than minimum. So especially if you're doing a lightweight development, don't aim for the minimum. Footsteps, moving furniture, any sort of hydraulic services, any sort of structure-borne readily noise complaints. We're constantly dealing with insurance claims, and when we assess them, we say, sorry, it's meeting code unless there's a specific development requirement that was anticipated or baked into the contract. There's really nothing that can be done. So we're really offering and recommending you aim a lot higher or a lot better. So There is a AAAC guideline on apartments that my firm and other firms have helped develop, and it sort of rates them in star ratings, and we'll get that into more detail. But it rates the impact criteria down at about a 2-star, and you could go all the way up to about a 6-star in terms of performance. So that's probably all from me from the intro. I reckon Aedan could probably step in here and talk a little bit about the North American market. Is that right,
Yeah,
Aedan?
yeah, that sounds good. Thanks, Joel. So, yeah, like Joel was mentioning, there's some similarities and a few differences between Australian acoustic requirements and in North America. But one sort of difference is that in North America, the up to 6-story building height is really dominated by lightweight timber construction. So I thought I would just start with a bit of a comparing the similarities and differences, and then we'll pass it back to Joel, and then we'll get into a little bit more about what is being done and what performance is kind of achievable with some of these buildups. So starting off, I mean, the UK, the EU, and Australia are all under the ISO standard for acoustics. The US, Canada, and New Zealand are actually all under the ASTM standard. So for airborne sound, that means that RW and STC are sort of the two crossover metrics. And for impact noise, LNW and IIC are kind of those crossovers. Now, one of the similarities is that the vast majority of noise complaints in both jurisdictions fall under that impact noise transmission class. And that really is the piece that lacks in building codes in many countries. It's not specific to one area. So there are a few more nuanced differences. The frequency range that is examined varies slightly from the ISO standard to the ASTM standard. But one of the bigger ones that I'll touch on is the ASTM standard has something called the 8 dB rule, which basically limits that single number rating. But I'll touch on an example that I think puts more context to that and sort of how these single numbers are determined. And then I think Joel and I can probably both speak to some of the challenges in a single number rating. So starting off the ISO standard, so RW, higher the number, the better. LNW is actually the opposite, lower the number, the better. ASTM has decided to make it both higher the number, the better. So basically, without getting into the nuance of that 8 dB rule, to get your IIC rating, you just take 110 minus your LNW. But then there is this challenge of a single number rating not really telling the whole story. And so in North America, they decided, let's actually have 3 single number ratings, because one single number rating we see is challenging. So let's just double down on the single number rating system, but now we'll have maybe 3 of them. These 2 aren't code required, but they are starting to be looked at in the acoustics community. And I think there is some benefit. It's better than just us having a one single number where you might be missing some information. So it's been broken down into, now there's these additional HIIC, or high frequency impact insulation ratings. The reason for that is that if you change your underlayment on a concrete building, you occasionally can actually double the thickness of the underlayment, and you might not change your single number rating, even though the high heel clicks have gotten drastically quieter. The high frequency is actually what that underlayment is helping with, but you might not be seeing it because it's getting drowned out in the single number rating. Conversely, for wood frame, you might be meeting code or actually be meeting a reasonable, well above code single number rating for your impact performance, but the low frequencies, 50, 63, and 80 hertz, aren't covered in either of those standards, whether it's LNW or IIC in North America. So this rating looks at those most low frequency data points and more heavily weights them. Now, there are challenges when we talk about low frequency. You're measuring these really large wavelengths and you're in a small room. And so you can have some challenges. So seeing what the minimum room volume is important for that as well, and for getting accurate measurements. I'm sure Joel has stories about trying to measure in very small receiver rooms in the field, but the ISO standard lays out 50 cubic meters as that minimum room volume. The ASTM standard has 80 cubic meters as the required and 125 actually as the recommended for any impact noise testing. What that means is that the point that you're getting to sort of a representative measurement where you have enough sound waves bouncing back and forth in the room to get a real representative measurement tends to be around 400 hertz for ISO, for the ISO minimum room volume, and 160 for the ASTM minimum room volume. So it just means that below that, you can get larger variations in that result. So that is one of the challenges that the industry faces as we try to develop better low frequency performing systems. Now to that 8 dB rule, this is actually one of the things that helps in North America prevent these really woeful low frequency performing assemblies. And the reason for this is that to get your single number rating, you actually, in both standards, sum up any deficiencies. So any point where your impact sound is above this reference contour is called a deficiency. Both standards have the sum of that having to be less than 32. But in ASTM, there's this extra rule of at no single frequency can it be more than 8 decibels above that contour. So this black curve here is where it's limited that single number rating because we have 8 deficiencies. So it's saying it's really poor performing down at 100 hertz. In the ISO standard, you don't have that rule. So you'd actually be getting IIC 46 in the North American test methodology, which is about an LNW 64. So you would not be meeting code there, let alone having any kind of good, I guess, comfortable assembly. But the single number rating would actually put it at a 54 because it's sort of under penalizing how poor that low frequency performance is. So I can pass it back over to Joel to get into a little bit on some systems, and then I'll go through a couple North American case studies.
Yeah, that's a great example, just showing 10 dB difference just by how it's actually rated. So I'm going to talk a little bit more about the single ratings, and Aedan's already sort of touched on that in terms of how problematic it is to actually measure it. So here's just a standard example where I thought, let's take a conventional system and then a lightweight system. Let's just have a look at how they perform across the frequency spectrum. So you got standard concrete slab. I'm not even putting anything on the surface, just bare concrete slab. And then with just a standard resilient ceiling, nothing special. Sorry, it's standard suspended ceiling, no resilience, no acoustic insulation. So that's sort of the minimum that we always see builders trying to push over the line with us. And then this is basically the deemed to satisfy code required timber joist system that's in the building code. So how do they compare? So this graph, just as a little primer, similar to what Aedan's talking about, you've got, if you can see my mouse here, you've got your low frequencies down the bottom here. That's all your thuds from bare feet, from children running, things like that. Then you've got your mid-frequency footsteps, and then your high frequencies from high heels and hard shoes and things like that. So the blue line here is the overall concrete performance. So it's showing that, and a lower number is better. So it's showing that in the low frequencies here, it's sitting around 60 to 70 dB, and then it's sort of following this dotted line curve, which is sort of like the averaged level to replicate an LNW 62. And then you can see here that because it doesn't have any underlay in it and there's no resilience, the high frequencies are more prominent. So you'd heal high heels more. But when you compare it to your lightweight floor, it is getting the exact same LNW 62. And if you were able to build a building that had a conventional building that went straight from a concrete straight to a lightweight, you would walk across that and you'd experience that in a totally different way. So here, this low frequency from this lightweight system is more than 10 dB louder. It's perceived to be louder. You're going to hear those thuds as people are walking back and forward, and that seems to cause a fair bit of annoyance. whereas generally it's fairly similar throughout the mid-range, and then it's a bit quieter due to that acoustic insulation in it.
And
Oh,
Joel,
sorry,
maybe
yeah, Aedan jump in, yeah.
one other point that maybe is probably helpful to mention to people is because the decibel scale is logarithmic, not
Mm,
linear. These changes that Joel and I might be talking about, and like 10 on 80 might not seem like that big a change, but because it's logarithmic, it's actually going to be a much more impactful perceived difference. So a good rule of thumb is a 10 decibel increase will be perceived as twice as loud. So anytime
mm.
we talk about that, yeah, it's double the loudness.
Yeah, that's right. Yep. Absolutely, and especially when you've got quiet background noises in apartments, something that's suddenly twice as loud can go from just being audible to intolerable. Like I can't deal with this, and so that's quite a regular experience. So then the next system for comparing, just to show the deficiencies of that single number, now it's a fairly well isolated concrete system. It's now got some acoustic insulation in the cavity, and it's got a timber floor with some rubber underlay. So it's a pretty conventional concrete that you'd see in a moderate to high-end apartment. And then in this case here, what I've done is got the standard timber joist ceiling, and I've put a resilient batten on top. Say, okay, what could be done to improve that? And I've sort of jury rigged the numbers to get the same LNW value just for comparison. But you can see here that they're both achieving 45, which is almost 20 dB better than what the building code would recommend as the minimum. And you can see here that in the high frequencies, all those hard sole shoes and high heels, they're basically equivalent. But there's enough isolation in the system now that you're barely hearing those, if at all. And then there's a bit of change through the mid-range where, because of the amount of resilience in the timber system, it's performing better in this case. But there's still a significant, almost 10 dB difference in the low end. So even though this is a good rating, if you were to get a 45 on site, you'd be very happy. There's still a big change in the perception of that sound, that it'd still be like, oh, doesn't sound quiet, even though it's a good single rating. So that's sort of just a word of caution. I might jump back to you, Aedan, before I get into some
Yeah,
single
for
number
sure.
comparisons.
So when we're talking about North America, I mentioned it's a pretty drastic amount that is being built in wood in that low to mid-rise here. And there's a couple of reasons for that, but a couple of the main drivers are it's a much more cost-effective way to build in a lot of cases at these heights. And the other reason is sustainability. So the government, both in Canada and the US, I mean, both, and I think it's the same in Australia, there's an affordability crisis and sort of housing crisis. So we need more housing stock delivered, and then trying to figure out ways to do that affordably and to do that sustainably, because the carbon emissions of building the amount of housing that would be needed if it was all out of concrete would be quite drastic, have led sort of the charge there. But from 1 to 4 stories, this is specific to Canada from the Woodworks group over here, but 1 to 4 stories, 88% of that construction is in wood. When you get to 5 to 6 stories, still 52%. So it's still the majority of projects at that height are being built in wood. That 7 to 8 and then 9 to 12 are where mass timber are starting to slowly take bits of that market share. Light wood frame in North America tends to be limited around that 5 to 6 story height per the building code for fire here. So the most common project type in North America is what we call here a 5/1. And that is 5 stories of light wood frame built over one concrete podium level. And you can't typically drive for more than 10 or 15 minutes in a North American city without seeing sort of, especially as you get to the suburb areas, this type of project. So I thought we would look a bit at what is being done on all of these projects here and comparing how the performance levels kind of end up relative to concrete. So these are just sort of some similar assembly comparisons like Joel was just going through. So I would say, status quo assembly that's been used for many years in North America is not great for light wood frame. I live in a wood frame building that has something very similar to that top assembly, and I can hear exactly what room the vacuum cleaner is in. If they're stomping around, you can tell what room they're in. So it's meeting minimum code here, just as it would be in Australia, but it's not performing very well, especially for low frequency impact noise. And that's what the data on the right is showing. So this is where having manufacturers that will provide the full data range and having consultants like Joel who are experienced at looking at the performance at those different frequencies really is the key to success. In single number ratings would tell you you're actually pretty similar, 57 versus 58. But if you look at that difference at low frequency, you're going from about 45 decibels up to over 70 down at 50 hertz. So that's kind of that drastic performance difference that can be challenging. And this is where those other single number ratings that North America have introduced come into play. So at least it gives you a sort of idea of these two assemblies aren't the same. So that wood frame assembly, if you just looked at the low frequency impact noise, is 44 versus 79. So the concrete you can now see is very high performing relative to the light wood frame. The high frequency, the HIIC rating, would say that the wood joist assembly is a little better. It's 6 points better than the concrete, but that's not where the noise complaints are going to be coming from. So gives a little more insight into that comparison. The other thing that's been a big move in North America in the recent few years, and I think other places like Australia, like the UK and parts of Europe have been much more advanced in this area, is not relying on screed. In North America, it's been very common to just pour screed toppings that often actually underperform relative to what the lab testing would say. But there's been a big shift away from that for a number of reasons, but issues with cure time or cracking, reducing the structural weight, and then new initiatives and code requirements to actually reduce the embodied carbon of these structures and keeping this mined cementitious wet material out of these wood buildings have been kind of a big focus. Same goes for mass timber as well, but even in light wood frame, this has been kind of a big focus. So the way that this is sort of being achieved is taking the other mass layers that you might have in this dry system and isolating those to a greater extent. So whether that's better isolating the ceiling, the gypsum board on the ceiling, and if you're adding mass on your subfloor, having that in dry panelized systems. So this is a comparison of a new sort of system that's been used on projects over here relative to the sort of status quo screed on a thin underlayment with isolation clips. So you can see that by going to the isolation clips instead of the resilient channel, it really is only changing that assembly below 800 hertz, but it's that low frequency that was problematic, and that's where the improvement has kind of been targeted. So again, sort of focusing your solution on the problem. We get a lot of calls, oh, well, can I just put a thicker rubber underlayment on top of the wood frame, on top of my wood frame assembly because I am having noise issues? But at that frequency, a thicker rubber underlayment is going to be limited in how low that improvement can help. Whereas isolating that ceiling or a thicker resilient buildup on top is going to be what lets it get to that lower frequency improvement. The other thing that's important is having not just lab testing, but also validating that expected performance actually carries through to the field. So lab testing is done in a very controlled environment. You can see the picture on the left, converting from feet to meters in my head, about a 3 meter by 4 meter area is used. And then this tapping machine taps down on your floor assembly. And then that lab receiver room measures how much noise there is. In the field, it's a very similar principle, but instead of this controlled floor area without any of these adjoining constructions like walls, which introduce flanking paths, you're actually in the building and everything together is kind of going into that. So when we compare that improvement from isolation clips in the lab to, this was a recent project where post-completion testing was done actually in the building itself. And you can see again, ceiling isolation clips help down at that low frequency. So the only difference here was the Genie clips on the ceiling compared to a res bar. And your single number rating, so the DNTW, or over here would be the AIIC, is about a 6-point difference. So the single number is saying there's improvement, but the low frequency impact rating is actually saying 13 points. So a much bigger improvement kind of targeted at where that problem was. Anything you want to jump in with now, Joel, or do you want me to continue?
Leave that slide up, because I think that's a really good one. And I think with especially with timber developments, it's looking at multiple points of isolation. So if the energy can get through that initial underlay into the actual joist, then similar to resting your ear on a table and tapping anywhere, the sound's just going to traverse straight through the joist, go right through all the structural elements. And we've even experienced noise issues that occur over 2 floors because it just gets into the external facade and wraps all the way around. So having multiple layers of isolation means that suddenly you get the benefit of that entire air cavity in that system, because the sound it travels down through the joist and then it's interrupted before it gets to another hard surface in a ceiling. So multiple layers of isolation could be above the joist, below the joist. It could be at party wall joins or at columns or beams. So it's starting to think about how do we keep the energy within the apartment itself, within each apartment.
No, I think that's the key here, is having those decoupled layers, like preventing the noise from then spreading through, and adding multiple different layers and locations of that isolation.
Okay, so even though there's a lot of things to look at in terms of the graphs and the spectrums, which we're going to sort of hammer home with recommending acoustic consultants. In the end, they're still going to end up talking single numbers. So single numbers are helpful to some degree. So here's a sort of a rough guide that we've put together, which is in terms of LNTW, LNW, lower number is better. So if we start up here, when we're up around the 60s to 65s, it's just a very noisy environment. Footsteps and everything is clearly audible and clearly a problem. And then as you slowly etch through the 50s, things are still audible. You can start to accept it, but we've had experience. People say, "Oh, yeah, less than 50. I can deal with that. I'm used to living in apartments." But it's really when you start to get below the 50 that the impact sounds are just audible and it's now comfortable. So this is a long way from code. So the next slide sort of talks about where the building code sits. So it's sitting right up in this noisy and unacceptable range. And then to the right here, I've got the star ratings. So we have sort of set the star rating at 2 stars around here, and it's not till you get to a 4 to 5 star, which is where we start to recommend. This is where you should sort of aiming to be starting for apartments, and then as you move into more high quality luxury apartments. We sort of get to about the 45 to 40, and you just get to a practical limit beyond which it's incredibly difficult to get anywhere beyond that until you go into a carpeted type flooring. So just as an idea of just how far can you push a system, we'll look at conventional first, just as a baseline. So if you've just got a 200 mil slab and you've got nothing above and nothing below, that's sort of sitting around this sort of range here. And if you put a slight little foam underlay on it with a hard floor, that's basically code compliant. So that's how poor you sort of have to work on to even get it there. And you've got to start to add rubber, and you've got to start to add screed or any sort of dry mass layers. And so you're sort of getting into a point where if you haven't got a ceiling in a conventional concrete system, you're really sort of limiting at this sort of acceptable range where you've got a heavy layer with some thick underlay. Comparison, obviously, as soon as you've got a ceiling, which is a lot more common these days with services, then you're already starting 10 dB ahead of the curve. So you're already code compliant with nothing above. And then as you start to add on the layers above, you're starting to get into a really really comfortable, peaceful environment. So now if we keep this system on the right and we add in a lightweight joist system, so this is still the single number comparison, not like what we were talking about before, but it's starting a little bit worse. And this has already got resilience in it and insulation in it. So when you start to add some underlays, you're starting to get into the tolerable stage with some heavy, whether it's screed or whether it's a dry mass layer. And so we're finding that trying to get up in around this sort of range here is quite difficult and needs a lot of coordination, needs a lot of extra mass and a lot of clever design. So that's for you architects on the line there to be thinking about that. And when we've tried to push systems into this sort of range as a hard floor, that's where the cost increases, and then we start to get clients pushing back and saying, well, hang on, this is no more cheaper than conventional. Why are we going down this path? So we really try to say, believe in the timber and come up with solutions. That's really what we're really aiming for here, and come up with some creative solutions. And Aedan's got some more slides on just the cost later in the piece. Did you want to jump in here before I go into something more about thinking about how you look for consultants, Aedan? Or
Yeah, sure. I'll go through the case study, and then we can go over to that. So yeah, this is sort of just one recent example in North America here. So this was a sort of master planned development. It's not too far from where I live on the west coast of Canada. And so it is a 5-building development. They range from 4 to 6 stories. All of them are wood timber frame. But it was delivering 590 rental units, and 60 of those are designated as affordable rental units. One of the other kind of pieces to this is that it's in a high seismic area, so controlling the weight of the structure was really a critical piece as well. So this is the assembly that was selected there. So the single number ratings, it was a LNW 50, RW plus CTR would have been 55. You can see that its limitation is still low frequency, but sometimes it can be tough looking at the curves relative. So I'll put it on compared to a 200 millimeter concrete in a couple slides. But this is where the weight savings were really important as well. So looking at the screed topping options, those were adding quite a bit of mass, between 31 to 63 kilograms per square meter, which the structural engineers were really challenged with. So instead, they added additional plywood layers, but that also has a carbon reduction piece. So the embodied carbon of wood, even if you don't take into account the biogenic carbon, which in North America, you're not allowed to count the carbon sequestration. So it's, I think, even more sort of enlightening when you look at it under the Australian EN calculations, but there it's still showing that we're reducing the carbon footprint of the building quite substantially by that specific comparison is almost an order of magnitude reduction. So then this is another assembly more popular in some of the European buildings that we work on. So it uses a recycled gypsum fiber board on top of the system. It's a wood joist with sort of a reinforced metal webbing. But you can see here using the dry laid genie board on a resilient dimpled interlayer there to prevent the vibration and impact from getting into the structure to begin with. And then also having isolation clips on that ceiling to reduce the sound transmission into that structural layer as well. So I thought I would just take those two systems and then compare them to a 200 millimeter concrete. So you can see, and this is just a standard, I think 2 millimeter rubber underlayment under a vinyl plank floor. So you can see that it's still, the concrete is tough to match at low frequency, but these methods are getting it much closer by decoupling those different layers. Then you keep it closer to that occupant expectation of concrete. Concrete then a little worse in those mid frequencies, very similar to the data Joel pointed out earlier. So that's just sort of the results of trying to gear that assembly towards those problematic frequencies. And what do those cost? So that becomes a very common question of, okay, we can do some things to improve it, but what's the cost going to be? And then does that push it back towards something else? So the costs that we tend to see for these products on local Australia projects, and these are in Australian dollars, $43 per square meter for that 25 millimeter recycled gypsum fiberboard, about $12 per square meter for using isolation clips rather than a resilient channel, and then about $4 per square meter for 2 millimeter rubber underlayment rather than, I guess, a foam. So I can pass it back to you, Joel, on a bit on the consultants.
So just, yeah, probably the last bit before we go to questions, which is just when you're selecting acoustic consultants, please ask for experience with previous timber buildings, but ask for their specific experience. Sometimes you'll get a nice, pretty brochure with all of the work they've done, but it might be their London office, not their local office. So that's and we find that they'll commit and say, yeah, we've done all these projects, but then their other consultants that have worked on those are busy, tied up. So it's trying to get who's actually working on the project, who knows what they've done, who's done it before. And so similar with everything, inexperienced consultants can under design or over design, which can all change the risk profile and also the cost profile. So there's a list, the AAAC lists the member firms, which are all bound by the code of ethics and sort of practicing their expertise. And some of the things that you're looking for, I'll just sort of flick through these quickly, which is trying to get acoustic consultant in very early, especially when you're considering set outs and layouts in terms of spatial allowances. We've had to come in, or we've come in late on a few projects, needed extra floor ceiling heights, and they've had to go back to council for extended building heights and things. So getting consultants in early, especially in lightweight, is really helpful, and getting them to coordinate with each other. Don't silo your consultants and just get them to write their own reports. Get them in around a meeting table, hopefully, or at least have planned for some more design, which just increases the fee. So it does cost more in the consulting stage with these lightweight buildings, but it results in a better building overall. One of the big things is whether you're asking a client or whether you are the client yourself, is really trying to work out at the outset what sort of quality are you trying to meet. So there's a bunch of different options here, which is obviously the minimum standard, which is something that I'd recommend avoiding. Sometimes that's just a necessary market that you need to meet. There's also the improved AAAC star ratings. Sometimes we just get a client will just say, whatever the conventional concrete equivalent is, we want to match that. So that's where you need to allow for more design and all that. Other times there's some very sneaky clauses in councils that'll require a certain star rating for a floor or a wall. And sometimes people haven't noticed until the DA's already submitted and approved. And then you start to get into design, you realize, oh, this needs to be a 5-star building. We weren't aware of this. And that's separate to Green Star. That sometimes councils, because the building code's so poor, have thrown in a star rating into the back of their DCP. So make sure you're aware of that, or the consultants are aware of that. And all of those things in terms of the actual quality plays out in terms of just spatial allowances. So it could be wall footprints, like floor ceiling footprints, and it can change regarding the type of timber construction, whether it's a cassette, whether it's hybrid sometimes with mass timber, with steel and concrete interwoven in it. You might have you might have some timber joists, but you might have some concrete columns. So there's all these sort of mixtures that you need to consider, and that plays out on your spatial allowances for your footprints. So that's probably all, unless Aedan wants to chime in. We can go to a series of questions, or if you want to jump back in again.
Yeah, wonderful. Well, first of all, thank you for that. That was really in depth. It was wonderful to get that tip-tacking and the global experience. I've got a question here that might lead us quite nicely along to our discussion on flanking. From James, he asks, low frequencies seem hard to reduce transmission. Are they less of a concern than high frequencies? Like, what frequencies are most common that cause a nuisance, like low, medium, high? It sounds like high is covered by the code and low is not, and that's the real issue here. Is that sort of the headline?
Well, I think and Aedan can step in too, but I think the high frequencies sort of take care of themselves once you get some resilience in the system, which is sort of expected. You know, we're going to have to put some sort of underlay in. We're going to have to have some sort of suspended ceiling, and so it's very rare that I find that we're failing buildings, or that they're not fit for purpose because of a high frequency problem. Usually that's where they've actually bridged some resilience, or they've installed the hard floor right to the periphery and connected it straight to the external, like to the walls or to the skirting. So as long as the isolation's in the system, the high frequencies take care of themselves. Low frequencies are where you need a lot of mass and a lot of careful design.
But a question from, oh, sorry, Aedan.
I would say similar. The only thing I would add is, yeah, like Joel said, is if it's an design, you have to design for the low frequencies. The failures tend to be the high frequencies, short circuiting of resilient channel. If you're hearing of noise complaints and it's in that higher frequency, they're saying I'm hearing high heel clicks or pet claws, then we typically see either the short circuitings or failures of one of the layers.
Yeah, they could have screwed through a genie clip, or just something sort of bridged it at the periphery of any element.
What do you find is the lag between a building being built and occupied, and when you feel sort of relief that the time has passed, there's not likely to be many complaints? Or is it so subjective that someone who takes occupancy down the line can be disrupted?
I've found it very. Sorry, you go, Aedan, first.
I was gonna say we tend to see it very quickly from a tenant. Like, hit people within their own expectations tend to know pretty quickly if it's meeting them or not. There can definitely be opportunities where one person just has a higher acceptance level of something, and then a new tenant moves in. But typically it's pretty immediate to occupancy of, sometimes it's as soon as someone moves in upstairs or moved in, or we've had it where fitness noise is a whole separate thing, but like the day a fitness room gets the equipment in tends to be the day of the noise complaint. It's pretty immediate.
Mm-hmm. Yeah, and it's changing more now, where more families are moving into apartments, and so as soon as you might have an elderly couple that's lived there for years, and they move out, a new family moves in, you'll get a call within a week. And so if it's still within that first sort of 7 years, they'll jump on it quickly. And if it's after that, then it's sort of up to the owners themselves. Can I fix my own ceiling to deal with this? Or we do some testing and strata gets involved, so it can get very complicated.
Certainly, yeah, and that seems to be the overall thrust, that complicated, that large gap between the code requirement and that clear incentive to build to the code minimum, but to at the not meeting the consumer's expectations as a result. Do you find any common details that are difficult to resolve that can cause problems for low frequency or even high frequency noise, like specific penetrations or inclusions of like certain appliances, or yeah, are there any like inclusions that have you thinking in a concerned way if a building has certain things included?
One that we see quite often is the sheathing, the structural sheathing on top of the joists, and whether there can be breaks in that or not. So whether it has to be continuous or if it can be broken, when from a flanking perspective, whether you can have a cut in that or not can make a big difference
Right.
in that lateral transmission. So that's one that we always try to figure out early on. I think that's back to Joel's point of having different areas be able to work together, because it's the structural engineer that typically is
Certainly.
in control of that decision, but it affects acoustics quite a bit.
Yeah, massive structural considerations there, especially if you go high.
And I think with the lightweight ceiling, if you think of it, and that's what I try to talk to architects and designers, is the lightweight ceiling is the acoustic barrier. So it's sort of understood that it's the fire barrier, but it's also the acoustic barrier. So if you're going to penetrate that and put like a return air grill in it, well, then that needs to be treated. If you've got a standard downlight, maybe that's okay. But if you've got one of the sort of heat lights in the bathroom, that needs to be treated. Whereas in a conventional build, the ceiling's helpful, but it's not necessary to get over the line. So I think that's it's a big part of it too.
Thank you. I've got a question from Josh, who says, do you have a feeling of how CLT floors compare to joist systems and concrete?
Yeah, there's actually something that WoodSolutions has, which I helped work on, is I think it's booklet number 43, which has a lot of CLT acoustic systems in there, and they show all of the different ranges from code compliant up to certain star ratings. That was a huge amount of work. TDA was involved in that too. CLT floors have more mass, obviously, than a lightweight joist. Where they are problematic is that most of the floor ceiling space is taken up by the CLT, and because it's lightweight, it doesn't perform as well as concrete. So sometimes the actual the benefit of having joists with a large air gap is that you actually get a fairly big acoustic benefit from that. So we've found that with CLT floor ceiling systems, we have to put a lot more mass above and a lot more resilience below than a conventional.
So many problems can be helped by adding a bit more depth in that floor thickness. They just solve so many issues. By the way, everyone, that's the WoodSolutions guide number 44.
44 is it? Thanks.
Acoustic performance. So definitely check that out if you're interested in some further reading. Question from Rob. Thanks for covering floor issues. Please, can you recommend some learning resources regarding external low frequency airborne noise in the retrofit for light timber frame?
Ooh, that's a good one. Aedan, do you have anything to come in there?
Yeah, so for retrofits on floors, was that the
Retrofit
looks like external.
External low frequency airborne noise.
so
it could be from
outdoor?
freight trains or aircraft or something like that.
Yeah, I mean, there's we do some structure-borne isolation for that type of like rail, but the airborne, I think you're getting mostly into your facade design, and the windows tend to always be the weak point there. So I don't know if you have any recommendations there, Joel, but I think upgraded windows tends to be a big one.
Yeah, that's right. And just generally, the classic, I'll just put double glazing in, can be problematic. If you've got a very small DGU type double glazing, you can actually go backwards in the low frequency. So it's about getting some depth. It's about getting that air cavity again. So yeah, when we're designing around airports and large sort of freight noise, we tend to have 100 mil, 150 mil between the panes. And then we're thinking about that in the lightweight space with your facade design. We're trying to get large cavities, resilience. We're basically trying to turn a floor on upright and building some yeah, isolation there.
Are there particular classes of clients or people that you find struggling with this a lot? And are there classes or groups of people that do really well with going Code Plus or recognizing these issues? Like new developers versus seasoned developers, or structural engineers versus some architects, native born versus international. Are there any people, yeah, is that
The one thing that we definitely see is that it can often take a bad experience to get people to be, I guess, attentive to the issue. So a developer that's had a noise complaint in a recent project then understand the value of going through the more detailed design, putting in the systems that have been recommended. But what we do often find is that you give it enough time and then there's some turnover at that development firm, and then the cost-cutting conversation comes back in, and then they'll sometimes fall back into those same mistakes that were made when the initial issue happened. So we tend to always see that once someone's had an issue and they want to do it right, they'll put in the right sort of products and systems, and then after enough time, they sometimes go back and repeat the cycle.
Yeah, I'd echo that. I think something that I've really enjoyed is working more with structural engineers, especially when it comes to like floor dynamics and floor stiffnesses. And especially if they've got a lot of experience in lightweight market, they're looking at trying to get that sort of footfall. I don't know all the terminology, but basically they're trying to get those resonances in those, whether it's a mass CLT slab or the lightweight joist. They're trying to get shorter spans than what's allowed by the code. And we find that when you've got the shorter spans, you get less deflection, so you get less creaks. It also means that all your resilience can start to work a lot better, because the resilience has to deflect at least more than what the joist is deflecting at. So structural engineers seem to take it quite seriously when they understand lightweight dynamics.
Great answer. Last question, potentially. How do you find that these thicknesses and section modifications are received by architects and designers? Like, there's always a massive push to decrease floor-to-floor thicknesses. How do you find that conversation goes? Do you find you mentioned that sometimes people can get unstuck by charging too far down one path with a narrow depth, and then finding out they have to undo all that hard work. Is that well known or poorly understood in your opinion?
Yeah, I think what I've found is if I can get in early, I'm always thinking about allowing for a maximum amount of floor build-up, so that the dry floor build-up can be seamless into the wet build-up, because it's not like conventional where you can just have all these various set downs. You've got to really think about, are we adding something above a joist or above a CLT, and how do we transition out to balconies? So that's if I answer your question correctly, that's the first thing that I'm going at, and that seems to be where things fall apart, where they haven't allowed potentially 60 mil, 80 mil of build up, depending on the quality of the apartment. So then that plays all the way down in terms of your floor ceiling total depths, and then also your building heights, and then also just in terms of your structural loads, how much mass are we going to be applying above and below, which then changes your joist depths and your structural connections. So that's what I find seems to come undone the most, is getting in as early as possible and making those allowances.
Beautiful.
Same thing. Yeah, you get early coordination and even having like a semi-accurate allowance. It's the painful ones are where it just wasn't accounted for, and then it's well into design, and it's like, oh, well, that's going to change your build-up height by 75 millimeters or something pretty drastic.
Well, I think that's a wonderful place to conclude. Thank you so much for being with us, Aedan and Joel. I'm sure the audience got a lot out of it. We got some great engagement in the chat and in the Q&A. This webinar will be recorded and put on the WoodSolutions website for future reference. So yeah, please join me in thanking Aedan and Joel for being here. And just head off, I'll close out by saying that WoodSolutions wishes everyone a very Merry Christmas and a Happy New Year. The Australian Timber Design Awards for next year will be open soon. So if you have any projects that will be of interest to be entered in this wonderful awards, then please keep them in mind as you enjoy your time off. And we'll see you in 2025. Thank you so much, and Merry Christmas. Ciao.